Hey everyone, thanks for joining. Data drift is one of the, I think, most common issues we deal with as data scientists when deploying models to production, but also one of the trickiest one to deal with. And it becomes doubly tricky when we're dealing with unstructured data, such as NLP or text data. In the next 30 minutes, plus some change, I'll try to outline an approach to not only detecting drift in text data, but also understanding what happened and what should we be doing about it. Just, does it switch? I think that's broken. Just a quick, I think the computer froze, sorry. Yeah, works. Quick word of introduction. My name is Noam. I lead the ML research team at Deepchecks, where we develop an ecosystem of tools for continuous validation of ML systems. I think we're best known for an open source product, aptly named Deepchecks, which helps data scientists and data engineers validate their models while developing. We'll be using a couple of examples from this open source repo during the demo at the later part of this talk. So we'll start by talking about what is drift and how can we detect it. Then we'll continue to talk about how we can do that for unstructured data. We'll break unstructured data into a couple of concepts, metadata properties and embeddings. And we'll finish with a demo showing how you can actually detect using open source code that you have drift and understand the source of the drift is. So what is drift? When we talk about drift, we usually talk about a change in the distribution of our features or our labels. And we usually break it into two different concepts, data drift and concept drift. Data drift is a situation in which the distribution of our features, the input features for our model, change for some reason. We can, for example, think, let's say we're a real estate firm, and we're trying to predict the rent prices for apartments here in San Francisco. So data drift would be a situation in which many young people are moving into San Francisco to work in tech. So people are building more small apartments or partitioning existing apartments to meet this demand. In this case, the feature apartment size is being drifted. The distribution in the population is changing. That does not necessarily mean you have a problem in your rent prediction model, because it could be that your model performs equally well for small and large apartments. In that case, you're probably OK. On the other hand, it could be the case that that smaller apartments are a weak segment for your model, and increased size for this weak segment is a problem for your model. You should probably retrain or collect new data. On the other hand, concept drift is a situation in which the joint distribution of the label as dependent on the input features changes over time. In case of concept drift, because actually the relationship between the label and the features is what we're trying to predict using our model, if we have concept drift, we must retrain our model in any case. In the example I gave earlier, concept drift would be a situation that, let's say, you can't build enough small apartments due to regulation or limited land or whatever other reason. So supply does not meet demand, and the prices of small apartments soar. In that case, the price for the same small apartment has changed alongside with a change in the distribution of the size of apartments. And in this case, you have to retrain your rent prediction model on new data, on the new prices. We can give another example, which is more related to the domain of text and NLP. Let's say we're trying to predict brand awareness and brand sentiment. So let's look for searches for the term Twitter and its correlation. Around the Elon Musk acquisition last year, many more people were looking for Twitter as a search term than before. If we use our old model of the world, that's some kind of data drift, so more people are searching for Twitter, but that may indicate positive sentiment. More people are looking for Twitter, maybe Twitter is hiring, people are looking for it. What actually happened is the big Twitter firing at that event. So the sentiment associated with these increased searches has changed. So what actually happened was a concept drift. More people were searching for Twitter, but it was for a new and different reason than before. I'll also use this example to illustrate that drift can be segmented. So here in the US, where Twitter HQ is actually located, people are still looking also in the old context of hiring, of looking for jobs. But outside of the US, it only reached the news as some kind of spicy news item, and people were only looking for it in the context of the firing. So the concept drift that we experienced happened more in the outside of the US, in this geography, than in the US. Before I go into how to detect drift, just a couple of words about what drift should we be looking out for. When we talk about a classic NLP model, and when I say classic, I mean deep learning models that were the only thing in existence up to half a year ago, where we actually have training data. We train a model on training data to predict the label. We usually want to compare the distribution of our production data, the data on which we are inferring right now, to our training distribution. Because if the distribution of our new data is like very different than our training data, then it's reasonable to assume that our model won't do so well on the new data. In LLMs, the situation is a bit more tricky, and I'll listen in on the talk by Josh Tobin from Gantry yesterday, and what was a very good talk, I must say, but I disagree on a specific point. He said that searching for drift in LLMs is useless, and I think that's not the case here, because in LLMs, it's right that you don't have training data, so you can't compare your production data to training data, but you have evaluation data. You usually collect some kind of data set, which you evaluate your LLM on, and you know in this data set it functions correctly. At least that's why you put it in production. So if your production data drifted significantly compared to that evaluation set, there's ground to assume that your LLM may not be doing as well on this new data, or at least you need to recollect your evaluation set, reannotate it, and make sure you're doing well. In both cases, though, you'll want to also monitor for drift in production. For example, let's say we have a production pipeline, and we have data from a month ago that we already have labels for, and we know that the model is doing well, or at least did well a month ago. And now we have some new data coming in that we don't have labels for. So we can monitor distribution of our current production data compared to this reference production data that we know performed well, and see how different they are. If they are very different, again, a very good reason to assume that something may not be well with our model, and we should inspect it and perhaps retrain. So, OK, how can we actually detect drift now that we said all of that? In the case of classic tabular features, numeric and categorical features, it's pretty well established. You have, for example, Kolmogorov-Smirnov or earth movers statistical measures or metrics for numeric data. You have Kramer's V and PSI, population stability index, for categorical data. And they give you a number, a scale of how much was the distribution of this feature changed between the two data sets, train and test, train and production, whatever. The thing is that drift does not always happen in a univariate way on a single feature at a time. Drift can also be in the relation between various features you have in your data set. And to detect that, we use a neat trick we call domain classifier, in which you train a model to try to distinguish between samples and tell us if they come from the reference data set and the production data set. We do that by taking two data sets, the features, and then adding to them a synthetic label. For example, 0 for all samples from the training data and 1 for all samples from the production data. We'll join them together into a single data set, do a train test split, so we have an unbiased evaluation, and train a domain classifier. If the domain classifier, which is just a model, it could be a random forest or XGBoost model, any kind of model, if this model can't tell the difference between train and test, it does not succeed in the task we are training it to do, it means probably we don't have any significant drift in the data set. On the other hand, if the model can succeed, does succeed in predicting what is the origin of each sample, it means that there is some drift in our data set that the model is detecting. And we can use the performance of that score, for example, the AUC or something based on it, to understand how much drift do we have as a measure. Also, if we're using some kind of random forest or XGBoost model, like I said earlier, we can use the feature importance of this model as kind of explainability, because the features the model is using in order to distinguish our two data sets are the features in which the drift is happening, even if it's happening in a cross or some kind of correlation between these features. OK, you're probably asking yourselves, so that was all nice, but it's for tabular data. So what do we do with unstructured data, such as text? So like everything in machine learning, we have to convert our unstructured data, be it text, audio, image, or whatever, to some kind of number or category or vector that we can actually work with. And the way we come up with for doing that is breaking the problem into metadata, properties, and embeddings. I'll illustrate what each one means shortly. Metadata, I think, is the easiest to understand. It's just any information that came together with your text about the way you collected your text. It could be the source of the text, for example, website it came from, the news source. It could be the creation date, or when this item was published. It could be demographic data. For example, if you're looking at Twitter, at tweets, then who said that, what country does it come from, age groups, etc. All kind of metadata about the text. Metadata is very good to understanding the population dynamics of your text. Does the population change in any way? And for segmenting what happened. It has two glaring disadvantages. A, it's not always available. You only have the metadata you have and nothing else. And B, it doesn't talk about the text at all. It's just about the population of where the text came from. So to actually say something about the text itself, we use what we call properties, which is essentially extracting tabular information from the text itself, like features. It could be simple features, simple properties, such as the length of the text, or number of special characters, or even a limited number of TF-IDF encodings. It could be linguistic parameters, such as language, number of nouns, and it could be more complex properties extracted from the text, for example, by pre-trained BERT models, such as sentiment, register, is the text toxic or not, and so forth. So essentially, we extract this set of properties from the text, and the nice thing is, we have a pretty exhaustive set of such properties, and we can detect drift in these properties. And also, if we found that we have drift in any of these properties, it's very explainable. So let's say we have drift in language, and we have more samples in Spanish in our new data set. We know right away what happens. We don't need any additional explainability measures. Of course, the disadvantage of properties is that the drift doesn't have to follow in the properties you defined. It could happen in any other dimension that you're not currently monitoring. And in order to cover that, we move to our final method, which is embeddings. I think most of you know what embeddings are, but I'll just quickly recap. Embeddings are vector representations of the text, usually obtained by taking values in the final layer of a certain model, NLP model. It could be the model that you are training to perform your own task. It could be some kind of foundation model trained to perform some kind of generic task. I think the best example nowadays would be, of course, large language models, which are trained on a very generic type of task. And you can obtain them either by yourself using open source or your own model, or using embedding APIs, OpenAI, Cohere, AI21, whatever. The important property of embeddings that we're using here is that similar samples are close to each other in embedding space and vice versa. These similar samples will be far away. That means that if we detect a shift in the distribution of the embeddings between our reference data and our production data, we know that some drift has happened. But of course, we don't know what happened. We just know that drift did happen. So to recap, the advantages and disadvantages of each method, metadata is really good for segmentation and tells us about the population dynamics of our text. But it doesn't tell us anything about the text itself, and it's not always available. Properties, on the other hand, are always available. We can always extract them, and they talk about the text itself, and they're explainable, but they're not exhaustive. The drift could happen in a dimension not covered by your properties. Finally, embeddings are more exhaustive. Usually, embeddings cover a lot of different underlying properties of the text, and they're very good for detecting drift and outliers. The biggest disadvantage is that properties are not very explainable. That means if you know that there was drift in the embeddings, sorry, I said properties. If you know there's a drift in the embeddings, you know that it happened, you know that something changed, but you don't know what. So in the demo, I'll be shifting right in, we'll show how you can use embeddings in a more explainable way. The demo is a pretty simple one, in which we'll use the checks defined in Deepchecks to detect drift in our data, we'll do it on a news classification example, the AG news dataset, in which we have news articles, and the section from which they came from in the news could be business and politics, science and technology, etc. So just let me switch to the demo. I'll also switch here so you can see what I'm doing. Great. So 2 words of apology. First, I won't be running the demo live because some of the cells here take like a minute or 2 to run, and I don't want you all to wait. And also, I'll be using an experimental branch of Deepchecks because some of the latest features I'm using here are not yet in the main branch. But everything here is available, both open source and the notebook. I'll make it available at the end of the presentation. You can scan a QR code and get it. So I'll skip all the data loading parts because they're not interesting and start here. You start by defining what we call, zoom in, cool. Better? Yeah, so we'll start by defining what we call a text data object, which is basically a kind of a wrapper or container joining together our text samples with our labels, and also giving us some information about what type of task we're trying to perform. In this case, text classification. We can take a quick view of our data set. We have the samples themselves, the news articles, and we have the label, business, science, technology, etc. Of course, before we can calculate drift for embeddings or properties, we have to calculate them both. In this demo, of course, I'm loading them from a preloaded, pre-computed store. But you can also calculate them yourself, like is shown here, the calculate different properties method, or provide your own properties and just attach them to the text. Same goes for embeddings. I'm using here pre-calculated embeddings, but you can calculate them by yourself or using pre-built methods within the open source package. Finally, I'll be training a XGBoost classifier, a very simple classifier over the embeddings, just so we have some model to give us a sense of what is our performance on the train data set and what is our performance on the test data set. I'm using here the terminology train and test, but it can also, as we're talking about drift, could be train and production, evaluation and production, or reference production and current production. So you can imagine all of these contexts applying here. OK, all that being said, let's compute the property drift. The syntax is pretty simple. You import the check. We call each component in the package a check. It tests for a specific type of problem in your models or your data. So you instantiate the check, and then we run it to compare between the train and the test data sets. So I think it was cropped a bit. I may try to refresh the window so it will be the right size. Yeah, better. So once you get the result, this result, by the way, could be exported to any way. It could be exported to an HTML, JSON. You can also have Pythonic values outputted for each check. But if you put it here in a notebook, it will just show you the display right away. And here we can see that in the property formality, we have some significant drift in which the test data set is way less formal than what we had during our training. Also, we have some drift in the length of the text in the data sets. So now we know something about what happened. We know there is some drift in formality, but we don't really know the details yet. So let's bring out the heavy guns and use embedding drift. Again, setting embeddings, you can also calculate them with a built-in method in the package. And let's run the embedding drift check. First of all, you get a score, which here uses the domain classifier I discussed earlier. Essentially, we're training a domain classifier to use the embedding space and try to distinguish between the train and test data set. And here, we got the model. The model succeeded to do something. It's not zero performance, but not a lot. So we have some amount of drift, but not a lot of drift. So we have two displays here, one showing us the origin of each sample, train or test, and one showing us the clusters that were detected. If we look about the clusters, specifically about these two, in the upper display, we see that they're mostly comprised of samples from the test data set. So these are essentially drifted clusters, are clusters that used to have quite few samples, but now have a greater amount of samples in the test data set. And if we can understand stuff about these clusters, then it will let us know what happened. And looking at the low display in the cluster explorer, I used quite a simple prompt to GPT 3.5 Turbo to extract the topics of each one of the clusters. You can, I don't have time to go into details about that, but you can see it in the branch, or you can ask me after this talk. So we used a pretty simple call to GPT 3.5 Turbo to generate the topics automatically, and we see that they're talking about sports. If we look at about the samples themselves, yeah, Manchester United, actually, really, most of the samples are talking about sports. Okay, so we know sports is a topic that was drifted. It's relatively new to the test data set. And if we think about it, it ties back to what we saw in the property drift, because we saw that we have a lot more informal samples in the test data set. And that figures, because sport reporting is usually way less formal than business, politics, science, and so forth. So what we saw on the surface with the property drift, we can now see the, let's say, the ground reason here in the embedding drift. And just a note, in this case, we actually have the label, so we know that we actually managed to do it correctly. We know that the section was sports. But even if we didn't have a label, we could use this method of embedding, clustering, and topic detection to understand what happened. Just to follow up and see, okay, so let's say we did get access to the labels. Does it follow through? What will happen to the model and to our performance because of this drift? So comparing, that's another check in the package, comparing the performance of the train on the train and test data sets, we see that the recall for the class sports has decreased more than the usual gap between train and test. And that also makes sense, because we know that that sports is drifted. We have more samples talking about sports in the test data set, meaning we have less of them in the training data set. So the model is not so good in predicting correctly this type of sample. Finally, we look at another check, which we call a property segment performance check, which tries to automatically segment the data into weak segments using our properties. And it can generate a couple of segmentations, but one of them is this one here, in which we identify that the model is doing way worse on samples of lower formality, which again makes sense, because we know we have drift in formality. We have a lot more informal samples in test compared to train, so the model is probably not so good in predicting on these samples. Also, remember we had drift in the average length. Average length and average word length are correlated properties in this case. And indeed, the model is doing worse on shorter samples. Again, because we had drift, because the model didn't see these kind of shorter samples so much during training. Just back to our presentation. I'll shift the source a second. Okay. So just again, this notebook will be also available at the end of the presentation, so we don't need to copy the URL. A couple of words about how you can use drift and where should it meet you within your workflows. So drift, you should be testing for drift in several steps in your development lifecycle. First, during development, or what we call testing, you'll want to test that your test data set or your evaluation data set is not that far off in distribution compared to your training data. Because if it is very far off, maybe that's your real world situation, but you should be aware of that, because you'll get very different performance on drifted data, probably worse performance. If that's something you care about, you'll probably also want to automate that using kind of a CI/CD mechanism or testing automation mechanism. Finally, in production, which is the most important place to monitor for drift, you'll want to monitor for the drift in your new samples. That's very important, because in many use cases, you won't have access to labels right away for new production samples. So monitoring for drift, for changes in the distribution of your new data compared to, let's say, your earlier data, is the first indication you're going to get that something may be wrong with your model, even before labels have arrived. Where can you log it? So first of all, you can use any kinds of tools, for example, Deepchecks, to detect and explain drift in your local environment, in a notebook like I showed in the demo, but you can also log that in a more systematic way, for example, in an experiment tracker such as Databricks MLflow, which you can log the drift results and the HTML results, the explainability plots we saw earlier in your platform for each new version, for each new experiment. And finally, in production, you'll probably want to use some kind of, to log the drift over time in some platform. It could be just computing the drift and sending it to Grafana. Could be using some kind of monitoring tool, shameless plug here, for example, our monitoring tool at Deepchecks, to monitor what is the state of your model in production and perform root cause analysis on what has happened and what's the source of the drift. Finally, a couple of words about what should you do when encountering drift. So, simplest solution, if you have labels in production and you have the resources to do that, you'll probably want to retrain your model. Because that's the best way to make sure that your model now can account for the new types of samples, so the new distribution that you have. But, like I said, in most situations, you won't quickly have access to production data labeling, because it takes time to acquire. Could be between days for certain use cases or months for financial use cases, for example. So what you can do is you can shift the distribution of your training data to reflect better the distribution you have in production. You can do that by downsampling, removing some features that are not very important, or removing samples in a way that will make your training data look more like the production data. Or you can add synthetic samples, for example, by an algorithm such as SMOTE to generate samples in the distribution you're seeing in production. Finally, you can change the way you model. Many models enable the option to give some weights, different weights to samples, so you can weigh your samples in a way that will make them represent the new distribution that you're seeing in production. Of course, all of this requires access to production data, but that's something I assume you have because you were able to detect the drift. Cool, so to wrap up, we talked about what is drift and how can you detect it. We dove deeper into unstructured data and how you can break it down into components, metadata, properties, and embeddings in order to detect and explain the source of drift. Just a couple words about what we do. So you saw the example of our open source package for the research stage. It can also be automated, and we have open source tools for testing automation, CI/CD. And we also have a limited open source tool for machine learning, for monitoring in production with drift, segment performance, and everything you saw here, but in a more complete way as a system. We also have commercial offerings for testing automation and for monitoring. If any of you are interested in hearing more about the open source solutions or commercial offerings, you're more than welcome to catch me after this talk. Okay, thank you everyone. Special thanks to my team, Nadav, Nir, and Harsh. Yeah, and feel welcome to grab some of the Deepchecks swag here on the door on the way out. Yeah, thanks. I'm open to questions now. There's a question here. They'll bring you the microphone so everyone can hear you. Okay, sorry. We can do I didn't see everyone.
Can you go to slide 7? Slide 7.
7?
Yep.
Just a second. There are many stuff here. 7?
The previous one?
This?
Yeah, this one. So, in production, you mentioned and compared to previous data. So, how is that different than compared to evaluation set or compared to training? So, what do you mean by that?
Yeah, the difference is in some use cases, you expect the distribution of the training data on the evaluation set and these kind of data sets to be different than production. For example, sometimes you want to balance your data set between classes in training and test, but production data would have a different distribution of classes, and sometimes that's okay. In these situations, you want to define a reference data set that is from the distribution of production data. So you can accurately monitor the changes between two data sets that are comparable, like earlier production that you know is okay, and later production that you want to test. So,
are you suggesting that the drift
in all cases, I suggest that the data set you're testing would be the latest production data, but the reference could be training data, it could be evaluation data, and it could be earlier time in production, depends on your exact use case and your needs.
Cool, thank you.
I think there was a question there.
Hi, Flora here from PlayStation. So we've been trying to compute data distribution for our data sets and train sets. But one of the problems with that is we have huge amount of data. But trying to get the data drift computation fast enough requires us to have a very low sample ratio. So I'm wondering how many rows or what's your sample ratio when you are computing those data distribution and significant tests, and how fast it is?
Mm-hmm. Yeah, so we usually use, depends on the use case. For tabular data, there's no, like the statistical methods I've shown are pretty fast. You can use, like, for example, 100,000 samples easily and get good results. For methods dealing with embeddings and extracting properties, you probably want to use less samples. We found out that in most cases, 10,000 samples are probably enough to get an understanding of how the distribution looks like and how the big trends in your data looks like. That doesn't hold, like, for example, if you're looking for data drift in labels and you have some very rare labels, you'll probably want to sample smartly and to use some different methods. You can look deeper into Deepchecks. We have a specific adaptation of drift for cases of very imbalanced data, which specifically measure small changes in the rare categories. A couple more questions here.
Can you hear me? I did have one question. The QR code you put in there is private. Is that
it's private?
Yeah.
Okay.
Is that how it's supposed to be? Request access?
It's not supposed to be. I'll share it in a second.
Okay.
Sorry.
That's okay. Thank you.
Yeah, there were two questions over here.
Hi, thanks for the great presentation. I have a naive idea after I listened to this section. So can we use this tool as a large language model evaluation tool? Because when you generate some of the text, right, you want to evaluate your generated text. So if you use this tool, the data drift tool, to compare the original training data set with the generated text, can it be viewed as a evaluation tool for large language models?
Yeah, I guess so. It will test only specific, like very general understanding of does the distribution of the embeddings look similar between the original data set and the one I'm generating? I would imagine. Yeah, but I think it's a good test because I think in a lot of cases you'll see that the distribution did change because language model outputs have a tendency to look a specific way.
Okay, got it. It's too general, right?
Yeah, well, but I think it's not comprehensive at all. But I think it's a nice test. I think it's useful.
Okay,
now that I think about it.
Okay.
How important is it to use the right embedding model, like a fine-tuned embedding model?
Come again? Sorry, I didn't hear the beginning.
How important is it to use a fine-tuned embedding model for this analysis?
How important is it?
Yeah, is it important, or can we use an off-the-shelf embedding model?
The example here, I used OpenAI embeddings, and it worked pretty fine. Like the embeddings by Ada to OpenAI are pretty good. I think in most cases you'll probably find better performance if you use embeddings of a model trained on your specific task, but that's not always.
I understand, but that also takes time to collect the right labels, right? Mm-hmm. To find, you need time to collect labels to fine-tune your model.
I definitely not train a model just to get embeddings, just to compute drift. If you don't have embeddings available for you for your own model, just use open embeddings or commercially available embeddings. We have time for any more questions? So there was a question there and a question there, I think. Ah, sorry, didn't see you.
Thank you for the great presentation. Right. Okay. So thanks for the great presentation. I think it is a great potential of the Deepchecks. We have a lot of use cases in our daily model training. So I have two questions for you. So first one is about the date. So usually when we do the check for the data shift is during the development. We have around maybe say 2 or 3 years of the data for available for the training. But the problem for the drift is at a certain time point, before this point, there is a data drift. And after that point, the data is quite stable. So we may want to just cut the data after a certain point, for example, starting January this year. This leaves us to the challenge of detecting the data drift along the timeline. So do you have this capability to detect the drift to tell us at which time point the data is stable and we should use that after that? The second one is you have a text and categorical variable and numericals. Do you have a capability to evaluate all those together and tell us which of them might not be good to use for the training? So that's those two.
I'm not sure I understand. So the final question was, so you have drift in a couple of features. Sorry, what was the question at the end?
The second one?
Yeah.
The second one is we use the combined features, like we have text and we also have numericals, categoricals. We want to have a function or the library that can detect all of them together to tell us
the overall drift?
Right. So we can just remove some of them regardless what type of variable they are. I think the Deepchecks has the capability to detect them, use different methods.
Yeah, you have separate methods for tabular, like for tabular drift and for NLP drift. But if you want to do it all together in one run, I guess you can join the embeddings with your numerical or categorical data and feed it all together to a domain classifier. And then you'll get a single score of how much drift do you have and what is the feature importance for the drift, meaning what feature contribute to the drift. Okay. That answers the question? I'm not sure.
So basically 3 pipelines. Mm-hmm. Do you combine them all together to have a comprehensive view?
You can do that. Like most cases, people have like NLP or tabular, and you can test it separately and get a different score for each one. Like that's the amount of my text drift. That's the amount of my tabular drift. But I was suggesting you can also join it all together and feed it to a domain classifier, to the multivariate drift check. Okay. Then you can get a single score for your whole data set.
Okay, sounds good. What about the first one? Do you have the?
Can you just repeat it quickly?
Yeah, so
like the end part.
It's more like along the timeline. At a certain time point, the data has a shift. Yeah. Right. So we are not supposed to use the data before that date. Maybe it's because of the concept drift, right? So we need to detect this time point.
How the way that it will look in a monitoring
No, in situation? The development. During the development.
So if you want to do something like that, you'll probably want to treat it for a second like a monitoring use case because you're trying to see drift over time. So set some kind of reference, for example, the beginning of your data, and then for each, like, do a sliding window computation and plot the drift as a function of time. You see this increase at a certain
That's what I'm thinking. So it's more like a looping over through the days along the timeline. So I'm just wondering if there is any more advanced or fast way of using Deepchecks to do that.
What I described right now would be pretty fast. Like you can just compute over certain windows. The tabular drift is pretty fast, so you can do it pretty easily. You can also do it using the monitoring system, and then it's all orchestrated in parallel in the background. But it's pretty easy to do. I think.
Yeah, this is the last question we'll take in the session. Sorry. Any other questions can be handled outside.
Okay, do you guys have a blog post or a white paper that mathematically describes this math that you came up with, or is it at this point more empirical?
Can you repeat? So I couldn't hear the whole question.
Do you guys have a blog post or a white paper that mathematically describes this method that you guys came up with, Or is it at this point a method that is more empirical?
So yeah, we don't have actually the domain classifier comes from an idea published by Uber in 2019 called adversarial validation. They use it also to detect these differences between data sets. We used it in a drift context, and we changed the name to a name we found a bit more explainable, that makes more sense. In our documentation, we have explanations about each one of our methods, how they work and how we implement them, but we didn't publish any paper about it. We have also blogs about it, of course, in our website. So you can go to our website or our documentation and look for it there. But for each specific check I showed today, there's a page of documentation telling what is the method we're using and how it's done.
Have you tried to apply this to a different data set and see its results? I wanted to understand if it generalizes as well. That's where I wanted to get to.
Does this method generalize well?
Yeah.
So the only way to actually know that is to use it on a lot of use cases. And as far as we saw, the answer is yes. But yeah, that's a very empirical observation. I found that most of the papers on drift test the wrong thing. So there's not a lot of good academic research for drift for production.
Thank you. Thank you, everyone.